Electric dipole in an electric field. A polar molecule or one with induced polarization like this, where electrons spend more time on the right side and we have positive charge distribution on the left side, has a dipole moment. So what is a dipole moment? If I have charge minus q separated by a charge plus q, the distance between them 2a, the dipole moment is the distance between the two charges multiplied by the charge q, 2aq, and it's actually a vector that points from minus q towards plus q. Okay, so in a uniform electric field, if I place an electric dipole moment P, so this is pointing from minus q to plus q, as you can see here, at an angle theta with respect to this uniform electric field, you will see that the positive charge will feel a force F, which is q times the electric field to the right, and the negative charge will feel a force minus q times the electric field, so it's pointing to the left. And because there's an angle theta between the dipole moment vector and the electric field, this force is going to have a component which is perpendicular to the dipole moment vector, which I call F perpendicular. So here I have a force couple, and this force couple creates a torque on this electric dipole moment. So how do I calculate this torque? Torque, by definition, is R cross F. So it's going to be equal to 2A times F perpendicular. So this is the pivot point right in the middle. So it will rotate with respect to this axis that goes through the middle of the dipole. And A times F perpendicular is the torque due to this one. A times F perpendicular is the torque due to the bottom force. So we have total AF perpendicular, 2AF perpendicular. So that's going to be torque equals 2A F perpendicular. How do I calculate F perpendicular? If this makes an angle theta with respect to horizontal, F cosine theta is the one that falls on the axis of the dipole, and F perpendicular is F sine theta. So that's this component here. So this is 2AF sine theta. And what is F? It is electric field times Q, 2AQ E sine theta. And 2AQ is the electric dipole moment, P. So it's going to be equal to PE sine theta. Therefore, we can say that the torque, the electric dipole moment vector P will be P cross with E. So it's the cross product between the dipole moment vector and the electric field vector, because its magnitude is PE sine theta, and it's going to be in the direction of the torque, which in this case, using the right hand rule, will be pointing into the page. Okay. Now, regarding the energy of this configuration, the work required to rotate the dipole through an angle d theta, I will call dW, is rotational work. It is the torque it feels multiplied with the angular displacement d theta, which is the perpendicular force dot product with the displacement it causes, F dot ds. And the total work done will be equal to the change in potential energy using work potential energy theorem, because we're talking about stationary charges here. The change in kinetic energy is 0. So if I calculate the final potential energy minus initial potential energy, it's the integral initial angle theta to final angle theta, torque d theta. This is initial angle theta to final angle theta integral torque, which is Pe sine theta d theta. So this will become minus Pe cosine theta. Derivative of cosine is minus sine, evaluated between initial angle and final angle. So this will be equal to P times E cosine theta initial minus cosine theta final. Because of this minus sign here, I have changed the order. This is theta final to theta initial. So it's Pe cosine theta initial minus Pe cosine theta final. Now if I define the potential energy of this system to be 0 when the angle is 90 degrees, then I will have cosine 90 is 0. So this will be minus Pe cosine theta final. So the potential energy will be equal to minus Pe cosine theta. That is to say, the potential energy of the electric dipole moment vector P in the uniform electric field E is minus the dot product of P with E. So you can see that the minimum in the potential energy will be observed when P is parallel to E, because cosine 0 is 1. I will have minus Pe as the minimum possible potential energy. And this will correspond to this configuration where I have this uniform electric field, which is produced by some positive charge distribution on the left, some negative charge distribution on the right. The positive charges feel attracted towards the right hand side, negative charges feel attracted towards the left hand side, and you can see why this is the minimum energy configuration, because the dipole moment has rotated to have the charges line up with the electric field vector, so that the requirement of the attraction between the charge distributions has been satisfied. Okay, so we talked about placing an electric dipole in an electric field. Electric dipole moment vector is defined as a vector that points from a negative charge q to positive charge plus q, separated by a distance 2a. Its magnitude is 2a times q, or the distance between the charges multiplied by q. If this electric dipole moment makes a vector makes an angle theta with respect to a uniform electric field, it feels a torque due to this force couple, which is given by the cross product P cross with E. And the potential energy of this configuration can be calculated by considering the rotational work done by rotating this dipole moment vector through an angle theta, d theta, integrated from theta initial to theta final. This gives me potential energy minus P dot product with E if I define the potential energy to be 0 at 90 degrees. And this gives me the conclusion that the potential energy is minimized when the electric dipole moment vector P points parallel to the electric field vector, when the positive charges are as close as possible to a negative charge distribution, negative charges are as close as possible to the positive charge distribution that creates this uniform electric field.